So let's now make some simplification of the model for classification when we are using multivariate Gaussian distributions. So one thing we can do in such case is to share the covariance matrix. So simply stated, we are using one covariance matrix for all samples from all classes. One important thing, however, to note is that we are not computing the covariance matrix on all data at once, because there is a big difference between the different data from different classes, is that the mean is not the same. So we keep the different mean for each classes. This is required. And we just share the covariance matrix. So the way to compute covariance matrix then is to compute the covariance matrix for each class independently. But then we are summing them into a single covariance matrix that is basically the sum of the covariance matrix for class I times the prior probability, or the estimation of the prior probability for class I. So we are weighting this sum according to the prior probability for each class, and that gives us the shared covariance matrix. This simplification allows us to go from, so for the means, it doesn't change, it's k times t parameters, but for the covariance matrix, we reduce by a factor k. So instead of having k different matrices, we have one matrices, but still that matrices is growing according to the number of dimensions, the dimensionality of our problem. If we look at the corresponding discriminant function, we have this thing here. We have the function hix, which is basically this function. We have x minus mi transpose, x minus mi here, and we have the inverse of the covariance matrix. So this is the same function with the difference that the covariance matrix here is common. So basically, this thing is the same for all classes, because we don't make distinctions between the classes. The different distinctions is between the mi, which are different for each class. So we have an element that is shared, and this element is in fact, when I'm just mapping this into a 1D function as a quadratic function, this is basically, so ax2 plus bx plus c. So this part here is basically that element. So this is the element that make it quadratic. And as such, by sharing this covariance matrix, we are falling back on a linear model. So we are, in fact, using a model which looks like more ax plus b in 1D. So basically, we have this formulation in multiple dimensions. So this is a linear model, a linear vectorial equation with wi transpose times x plus wi0. So this is basically the a and the b of this kind of equation. And here we have wi equal to inverse of covariance matrix times mi. So this is different for each classes. And we have the constant element here, which is different for each class, but basically can be computed only once over all samples, where we have this component that is coming from expanding this, but keeping all the elements that are not function of x, plus log times the prior. So if we compare linear and quadratic discriminant functions, we see here that we have this kind of thing. So what we call a LDA, which is a linear discriminant analysis. So basically it's simplifying. We have these points here. And all you need to interpret that these plots is that the points are not, I would say, following the same distribution here. So they have different covariance matrices. But if we simplify, we just, okay, let's compute this, assuming that they have the same covariance matrix. It will give us a model where we have a linear model here, which is splitting the space that way. Everything on that side is from the class of blues. Everything on that side is from the red class. So, and we also assume that the prior is 50-50. So this is the kind of result we obtain with the LDA, linear discriminant analysis. While using a QDA, quadratic linear discriminant analysis, This is where we are not sharing the covariance matrix. We are using a different covariance matrix for each sample. And in such case, the model would rather learn this thing. And this thing will be better in the sense that it will better classify the samples, the red versus blue in that case. If we look at another case where we have this kind of distribution for the blue, this kind of distribution for the red, if we are again using a linear model, which kind of share the covariance matrix, so which is making a simplification, the decision frontier will be like this. Obviously, it's not super great, but it's still the best we can do with the linear model. And with the quadratic model, we have this model, which is interesting. So that means that everything in that region is from the class of blue, but likewise here it's also from the class of blue, because you know that class is kind of spread that way. So it's normal to see that in that region it is blue, and it is also blue there. And likewise for the red, you know, it is spread that way. So it's normal to see that here and there we are in the red region. Now, if we are looking at more cases, we still have the same thing with the LDA. We've got this kind of cut because we share the covariance matrix. It seems kind of obvious that it is not good. Why, when we are using quadratic model here, we can see that we are really circling the small, the grouped blue class. Now, another case, which is kind of interesting, this is where we have three classes. So one distribution per class, we have the red, blue, and kind of yellowish version. So with a linear discriminant analysis, we can see that we are splitting between the, not yellowish, the purplish. So we have the purple region here, we have the blue region here, and we have this split between the blue and red, and we have that split between the purple and red. So this is with the linear models. We see that the frontier are linear. If we are using quadratic models, we can see that the spread is different here and different there. Now we can make a second simplification. We can go on with a naive Bayes classifier. So in that case, we are assuming that there is no covariance. You know, all elements out of the diagonal have a value of 0. We don't have any covariance between the variables. All the variables are independent. So we say naive Bayes because it is kind of naive to assume that all variables are independent. In real life, it is kind of rare that we've got these things, but yeah, this is an assumption that is quite interesting. So here we still use a shared covariance matrix. So we are still making the assumption that we are sharing the covariance matrices, but we are imposing a further simplification where we don't have any values out of the diagonal. And so the discriminant function corresponding to that is what we call the naive Bayes classifier based on these two assumptions. And it's kind of simple function that is relatively easy to understand. We are computing we are evaluating the difference between the xj and the associated mean value for class I, divided by the standard deviation for variable j. All this is squared, so we are summing this for all variables. It's basically looking at how far are we from the mean value for that variables, normalized by the standard deviation, and doing this for dimension 1, 2, 3, 4, 5, up to dimensions. So this gave us some kind of distance to these mean values, plus the prior log of the prior here, which is required if we don't have equal prior probabilities. So here we are making a good improvement in terms of the number of parameters. So far we had d times t plus 1 parameters to estimate. Given that we are using only a diagonal matrix, we only have d parameters to estimate. So the scaling is now linear according to the dimensionality, no more quadratic. So this is a good thing in terms of reducing the number of parameters. A third simplification is to make use of what we call an isotropic covariance matrix. That means that the variance is equal over all variables. So all the variables have the same variance. This reduces us from a what we call a Mahalanobis distance we saw before. It is basically like saying that we are using a Euclidean distance. So how can this be possible is the fact that all values are the same on the diagonal. This allows us to convert the covariance matrix to simply multiplying by 1 over sigma square. And the rest is basically something that can be simplified as Euclidean distance. So it's a way to fall back on some kind of Euclidean distance here. And as such, the corresponding discriminant function will be this. So it's basically the same that we saw before with all the simplification here. It goes to something kind of simple. And we made a fourth simplification. We assume that the prior are equal. So the a priori probabilities are all equal over all variables. So PC1 is equal to PCJ. This allows us to get rid of that thing because it's the same for all. So we just focus on that element. And so given that the S here are the same for everything, so it's not changing from one classifier to the other, we can really simplify everything by using only the Euclidean distance square. So this is what we call the nearest mean classifier, because basically it is computing the Euclidean distance between the X and the mean of class I, and we do this for all means, so all mean values for all classes. And we use the square value because it is simplifying, it is not that important. And given that we are looking at the highest value for the H, we need to put a minus sign here to select the maximum value, which is in fact the minimum distance. And as such, we are getting here the nearest mean classifier, which is assigning samples to the class for which the mean is the closest to our sample. So looking at the nearest mean classifier, we have this thing. We have hi of x, which is equal to minus Euclidean distance square between x and mi, so the estimation of mean vector. If we expand this a little, just converting the Euclidean distance into some kind of vectorial operation, we have x minus mi transpose times x minus mi. If we just kind of shuffle these things, expand again this product, we have x transpose x minus 2 mi transpose x plus mi transpose mi. As x transpose x is common among all hypotheses, we don't care about this because this is constant for the classes. We can just state that our hi is equivalent to a linear model. So this linear model is wi transpose x plus wi0. So the factor for the part multiplying the x value is basically to state that mi is equal to wi is equal to mi. So we are using the mean vector here, and the constant is basically the norm of mi. What we call the norm is basically to sum the values squared, and so minus 1 over 2 the norm squared of mi, the L2 norm in fact. So with all these simplifications, we can go from, okay, with quadratic model, we have no simplifications. The covariance are not shared. So we have distinct covariance for each classes. So if we are looking at this distribution, so we are working in 3D. So this is more complex to visualize. See, all these points are kind of normal distribution in 3Ds. And yeah, basically they are grouped all together. We see here what you can see as the gray shape here is this really the decision frontier, the plane that is separating the samples or maybe the region of the class of blues versus the region of the class of reds. So this is the kind of the separating a hyperplane, but in 2 dimensions with a quadratic model. So this is kind of fancy, but yeah, probably a good separation. If we simplify to a linear model, and then you remember that we are using the fact that we are sharing the covariance matrix, this gives us this kind of hyperplane that is really cutting this thing sharply. So we are kind of cutting the space into sharply. One side is the blue samples, and the other side is the red samples. And if we are looking at the nearest mean, it looks kind of similar, but yeah, we don't see much difference here. Yeah, the orientation of that plane is slightly different. It's subtle, but it's not that different. In fact, we can see the difference according to the prior probabilities. So here we can see that we get only 1% of samples from the class of blues and 99% of samples from the class of red, so class C1 versus class C2. So in such case, we can see that the separating hyperplane is getting really closer to the class of blues. Why? Because with such imbalanced cases where we have much more red samples, the optimal placement of the hyperplane in terms of performance is better when we get closer to the blue samples, because even though we are closer to the mean, we have so much samples here in the red regions, it's better to move it that way closer to the blue regions. When it's 50-50, it's really at the center, in the middle. We can even look at, in fact, if we are taking the means here and we are computing the distance perpendicular to the plane between the two samples, it will be equidistant. It will be really at equal distance between the blue and the red here, assuming everything else that we saw before. And if we go the other way around with 1% coming from the reds and 99% from the blue, it's the opposite of the first case on the left. The hyperplane is really close to the red samples. And if we look at the effect of the prior probability, a priori probabilities here, we can see that the quadratic function is kind of moving. You know, in that case, we are still around the class of blues. We have similar shape here, but it's kind of closer to the red samples when we are in balance with 99% coming from the reds and 1% from the blues. With a linear model, we can see that that hyperplane here is really in between, while here it is really close to the blue ones. With the nearest mean classifier, there are no differences. We can see that that hyperplane here is the same than that one, even though the priors are different, even though we think that it is better to get closer to the blue samples, given the assumptions that we've made, including the fact that the priors are the same for all classes, we don't make differences. So that hyperplane here is basically the same than that one. So if we look at the different variants, we can see that with a shared covariance matrix with isotropic densities, it means that all variance is the same over all variables. We get finally a covariance matrix, which is basically the standard deviation, which is the same over all variables. So we've got sigma I over the diagonal, sigma square, sorry, over all diagonal, which is one parameter for the covariance matrix. So this is the simplest case. This is the case of nearest mean classifier. If we get into shared covariance matrix, and what we see densities aligned on the axis, basically no correlation, no covariance between the samples, sigma ij equal to 0. We've got d parameters, and that gets us with something, again, quite simple with less parameters. If we are sharing the covariance matrix, so sigma for class I is equal to a single sigma, we have d times d plus 1 divided by 2 parameters to estimate, which is growing quadratically according to the dimensionality, so that might be an issue. But the model here is linear. Still, we have an hyperplane that is splitting the two sharply. While when we have different covariance matrix over all the classes, so a different sigma I for each class, we have k times the covariance matrix, which is d times d plus 1 divided by 2. And this is the most general case we can get with multivariate Gaussian distribution for classification. Now we can do some tricks. We can rewrite the covariance matrix here in that way. We can, so in fact, we have a new matrix, covariance matrix, which is sigma I prime. And this sigma I prime is basically a composition of the first case where we have an isotropic covariance matrix with only single sigma for everything, which is really the simplest version of the covariance matrix. So alpha times this plus beta times the shared covariance matrix. So basically a full covariance matrix, but shared among all the classes. And we have the last case where we have a distant covariance matrix for each class, which is 1 minus alpha minus beta. So alpha is equal to beta is equal to 0. So we have a quadratic discriminant here. So this is the case where we'll just get rid of that, and this is equal to 0. So we are using directly the individual distant covariance matrix per class. So if we go with another, so this is the case where we get the most flexibility. There is no regularization here. So if we go with alpha equal to 0, so we don't care about that, but beta equal to 1, that means that this thing is also equal to 0, and we just use the shared covariance matrix. So this boils down to a linear discriminant version of that. And the last case is when the alpha is equal to 1. So this is equal to 0. This is also equal to 0. We only have this. This is a linear discriminant with shared isotropic covariance matrix. Nearest mean classifier if the a priori, the prior probabilities are equal. So this case is, I would say, the other extreme in terms of simplicity. The nice thing is that we are able to adjust this alpha and beta between 0 and 1 and get various intermediary version of that. So that can be seen as a way to regularize the model. So optimizing, having non-zero values for alpha and beta, get us with simpler model compared to the basic one with individuals covariance matrix over all classes. So we can take into account in our optimization the fact that we can regularize the model by adjusting the alpha and the beta.